Probably. I hope he's not trying to teach me material the day before. Yep.
Welcome back to Control System Lectures. Now, I have several videos right now on locating both on how to plot
When we were waiting to get back to the car, when we were waiting for it to snow.
Anybody have any questions? Questions? What's coming up?
How many questions are going to be on the exam? That you might have already mentioned.
Questions? Usually I like to give like 75-minute
Mhm.
hour. I like to give 4 problems with A and B.
Okay. All right.
So it's kind of like 8.
Pretty balanced, yeah.
Other questions you have?
You said 4 problems for the test, parts A and B, B, B.
What I said was that usually the style of the exam is much like the first one. I think there are 3 or 4 problems. Probably 4. What it says sometimes part A and B. So that's what to expect. That kind of thing. And try to make it be independent of A so that you can still do it correctly.
No.
Any other questions you have? I posted the homework 6 and 7. Not all of 6 and not all of 7. I have them here. I have to scan them and put them in. And so I should have all the homework posted today. I have office hours. Today I have to go. And so I have office hours from after this hour until 1:15. Okay. Any questions?
What will the test cover? Test cover chapter 6?
It covers chapters basically 6 and 7. I gave the what do you call it review. It's on the web courses. So it is there. These are the sections of 6 and 7. Of course, you may have to apply the Rouse Perret stability criteria because it's basically associated with the root locus. So that does come from, I believe, chapter 5. There's some things that, background that you have to know in order to get these things done anyway. Any other questions that can?
Yeah, for the formula sheet, you said it has to be normal size writing.
Yeah.
Does that mean you have to handwrite it, or can we like?
You can. It can be a Word document.
Can we like write on a whiteboard and then just take a picture of that whiteboard and then print out that picture?
If that's the way you want to do it.
Yes.
But normal size writing, don't make.
Not like the 6 font.
Don't compress 5 pages onto 1 page, that kind of thing. Just front and back. Front and back. This is two sides, right? Yeah.
In addition to that, are we allowed to bring the one that you gave us from last test?
No, just a new one.
Okay.
Any other questions?
So we need to do an example of not the where you cancel out the pole and the root, but the other example. I forgot what it's called.
Second method, first method.
The first method.
So.
With the triangles and the law of sines.
Yes. Yeah, that one.
The one with the triangles and the law of sines. It's a line and the bisection and all that.
How about if I just share the homework?
Okay.
That's homework.
That's fine, and I'll do the homework.
So, I have just, but it's really just a matter of applying the sine law, so the law of sines, to two triangles which are not right triangles. Basically, that's the idea. So, yeah. So, I think this was the open loop transfer function GCG 9/SS plus 3. And okay, that's the closed loop transfer function, but we're trying to, and that's just the let's see. This is without compensation, right? In other words, pure gain type of compensation, actually. And in other words, k equals 1. Okay, and so this would be the closed loop transfer function. But what we want is a closed loop hole at this location here. The problem is this is 2. This is 1. So see that we're given the damping ratio and on that natural frequency of oscillation, 0.5 for the damping ratio and 3 for the on that natural frequency of oscillation. And so using those two, we can find the desired closed loop transfer function pole, right? In other words, for a second order system, you know, the denominator is s squared plus 2 zeta omega n s plus omega n squared. And so with a zeta equal 0.5 and omega n equal to 3, what we get is s squared plus 2 times 0.5 times omega n, which is 3 s plus 3 squared is 9. We get s squared plus 3s plus 9. And you know the roots, you want to find the closed loop transfer function pole which is a solution of this. And you know that in general, if this is equal to 0, the S1 and S2 are minus zeta omega n plus and minus the j omega n times the square root of 1 minus zeta squared. And so you're plugging in these values, you get minus zeta omega n, so that's just going to be 1.5 minus 1.5 plus and minus j. And this is going to be equal to 1 over square root of 2, so it's omega n is 3, so it's 3 over square root of 2. So that would give you the 2.59. Okay, and then this problem is really much the same as the example problem. Okay, And so the angle efficiency there is 40.9. And so in this second method, you draw and here's your desired point right here, minus 1.5 plus j, 3 over square root of j. And you draw a line from the origin to that desired closed loop transfer function pole. You draw a line which is horizontal, going through that point P, and then you bisect this angle here, and this is the bisector there. And then you go phi over 2, where phi is that 40.9 to both directions. Okay, so it's 20.45 or so. And then you've got two triangles here, this one and this one, neither of which is the right angle, right triangle. But what you do know is that this angle in here, you can determine that angle, right? It's going to be well, you can determine this angle first, and then you can subtract it from 180 to get this angle here. So this angle in here is going to be just the arctangent of the imaginary, of the real component. So this is going to be the arctangent of 3 over square root of 2 divided by 1.5. And so that gives you this angle here. And that would be, I think it turned out to be 60 in this case. And so this is 135. And so this is, if you bisect this, then this here will likewise be an angle of 60 degrees in here. And this length here will be 3. You can see that just by applying the Pythagorean theorem. That's the square root of the real imaginary component squared. So you've got 3 halves squared plus 3 over the square root of 2 quantity squared. And so this is not 9/4 plus 9 halves, or 18/4, and 9 is 27/4. Let's see. So is that true? Minus 5, 3 halves squared, 3 over square root of 2. This is 1 over square root of 2. This is 3. So this is 9 halves. 9/4 is equal to 9 plus 18. Which is we take the square root of that. Square root of that is 27 is 3. So it's 93. Square root of 3, 2. So I don't believe it turns out to be what do you call it, 3? Mistake here. But whatever this length turns out to be, this length will be the same. This will be 60. This will be 60. And so you can, based on knowing this length here and these angles in here, this angle, this is 60, so you can find that angle in there. And so you can apply the law of sines to that in order to determine this length here. Okay. And what you know is that this is 60, this is 60. These are three. This triangle is an equilateral triangle. And so you know this length here as well, because it's the same as that length there. And if you know that length and you know this length here, then you can determine that point there. Likewise, you have this triangle here. You can determine that you know this angle in here, you know this angle here is 60. Is 60, so you can determine this angle here, right? You can determine that angle there, 180 degrees in the triangle. And so you can apply the law of sines to this triangle here as well, knowing this length here, and knowing this the angle here. You can determine the and this length, this angle in here, together with this angle here. Let's see. So we apply. If we want to find this. If we know this length here and this angle in here, which we do, and we know this angle here, then we can find that length there by applying the law of sines. And so if we know this length here and we know that point, we can get that pole there, and that gives us the pole and zero of the compensator. So it's just a matter of some geometry that's involved in this kind of a problem.
Would you say we need to be able to apply this method?
Pardon?
Would you say that we need to apply this method to the test?
You should be able to apply both methods. This is for lead compensation. Any other question you have about what to expect on the exam? Okay, so what I'd like to do is just talk about the graphing rational functions of the complex variable s. That's what we started out the last time. And so, let's see. And so remember, what we're talking about is mapping from a complex plane to another complex plane. And we started out by saying, okay, we can easily map from a real line x to a real line f of x, right? And we chose the example of x squared. And so for every point x, real line x here, we can find a corresponding point f of x down here. So this constitutes a mapping, right? We don't have to, use the conventional yx. We can just map it, a real line to a real line. Okay. So the next step up is to consider mapping from the complex plane, the S plane, and the S plane has an imaginary component, that's a j omega, and a real component. Mapping from the complex S plane to the complex f of S plane. So in other words, we would be given some function f of S, and we would be given, well, some path in this S plane. Notice that when you're talking about mapping from the real line to the real line, the path is pretty much dictated. You normally take increasing values of x to get the corresponding f of x. Down here, there is no clear path to map from this complex plane to this complex f of s plane. This would be the imaginary of f of s versus the real of f of s. Okay. And so it really depends. The mapping here depends on the application that you're considering. For example, if you want to run a frequency response, right? Let's say that you have a system, a closed loop control system, and you want to run a frequency response on the open loop transfer function G of S, what you do is replace S by J omega, and you let omega take on values that are positive, right? So, when you run a frequency response, you consider values of omega going up the J omega axis here, and you map, into the, in this case, we would be mapping from the J omega axis here to the G of J omega, right? And this G here is a ratio of polynomials, so it's a rational function, right? And so for every value of J omega, there is going to be a complex value of G of J omega. It will be complex in general, and so it can be expressed in terms of the magnitude and the phase, G of J omega, okay? And so for any given value of omega, as we move up the imaginary axis here, we can determine the magnitude and phase of G of J omega, and we can then plot it, okay, in this complex G of S plane. And so we can either plot it that way, or we can just plot what we call the Bode diagram, right? We've done the Bode diagram. You know that, again, the omega increases from very small to very large, and we plot the magnitude versus frequency on the logarithmic scale. That gives the Bode diagram of magnitude, and we plot the phase versus frequency on the logarithmic scale. That gives another Bode diagram of phase, right? So, these are cases in which we let S equal J omega, and we move up the J omega axis. If we're considering closed loop system stability, right, we want to determine the stability of this closed loop system here, then the path in the S plane is not only along the J omega axis, but it goes up to J infinity and encloses the whole right half plane, right? So this, you could break the axis here. This would be an infinity, right? And you consider this closed contour, right? And this point down here would be minus J infinity, and so you could start anywhere. So let's say you start here. You go up the J omega axis all the way to J infinity. You enclose the whole right half of the S plane. This is the S plane here, okay? And then you go up the J omega axis again. And so notice one thing about this is that a point here is the complex conjugate of its mirror image down here. Likewise, a point here is the complex conjugate of its mirror image down here. And so really, if you map just the upper half of this contour into the GH, in this case, it's we're mapping the upper half. All we have to do to get the complete closed contour for G of S is to take the mirror image of what we got when we mapped the upper half. Okay. Okay, but the point here is that when we're talking about stability, not only do we want to go up the j omega axis, which is basically a frequency response, but we want to enclose the whole right half plane and go up the j omega axis back to the origin again. So this contour here encloses the whole right half plane. So we'll be using this particular contour when we talk about stability. And I can give an example here for this particular case. Let's say that we have a g of s equal 1 over s plus 1. And we have this closed loop system here. We can easily determine whether this system is stable or not just by finding the closed loop transfer function and looking at the poles. Okay. In other words, the C of s over R of s is equal to G over 1 plus GH. The H is equal to 1, okay? So this is equal to 1 over S plus 1, and we're dividing by 1 plus 1 over S plus 1. Okay, so this just gives 1 over S plus 2. That's the closed loop transfer function. And you can determine whether the closed loop transfer function is stable. You just set the denominator equal to 0. Right? The pole is at -2, so the system is stable. Okay, but this Nyquist diagram that we'll be talking about allows us to, use an alternate method for determining stability. Okay. But for now, what I want to do is just map the points on this closed clockwise contour into the G of S plane. Okay. So what we need to do is run a frequency response from 0 to infinity. Okay. And basically that's it, right? So let's do that. If we have the magnitude, this G of j omega is equal to, replacing s by j omega, the magnitude would be 1 over the square root of 1 plus omega squared, and the phase would be minus arctangent of omega. Okay, so this is magnitude, this is phase, right? Replacing s by j omega, got 1 over 1 plus j omega. The magnitude of the quotient is equal to the quotient of magnitudes. So this is the magnitude, and the phase is the arctangent when you replace s by j omega of the imaginary over real, so that's just arctangent of omega over 1. So then we can plot this, right? We can...
Professor, why is it tangent negative?
Sorry?
Why is a negative sign on the tangent?
Oh, because it's denominator factor, right? In other words, we have 1 over 1 plus j omega. Okay. Yeah. And then, so let's plot this. Let's take some values of omega, and then take values of the magnitude of G of j omega, which is this right here, and phase, the phase of G of j omega. Okay, this is the phase right here. This is the magnitude, right? So if we run a little frequency response at 0, we get, well, and replace this omega equals 0. This gives you 1. This gives you 0, right? 1, 0. So then several other points. 0.1, it gives you 0.995 at an angle of -5.7. Okay, at 0.5, we get 0.89, so it's getting smaller magnitude, and the phase is getting larger in the negative direction. Okay, and then we take 1, It gives us 0.48, 0.707 actually, because 0.707 is 1 over square root of 2, okay? And the phase is going to be minus 45. So you can see that the phase is increasing from 0 towards minus 90, right? And then we have 2, 0.48, and the phase is minus 63.4. We have 5, we have 0.2 for magnitude and minus 79, okay? And 10, we have 0.1 and minus 84.3. And let's say we have 100, we have 0.01, and the phase is minus 89.4. So you see that the magnitude is getting smaller and smaller, and the phase is getting larger in the negative direction towards minus 90 degrees. And now we can plot these points. So basically what we're doing, we're plotting points, omega equals 0.1, 0.5, 1, 2, 5, 10, 100, and so on. We're plotting points along this segment of this closed contour into the GH plane. So in the GH plane, I'll put it over here, we start out at 1 angle 0, and then 0.9 angle minus 5.7, right? So it's something like this, and then we'll get more points looking like this, right? So all you're doing is mapping polar coordinates, right? And so as omega increases from 0 to 100, this is looking like this, right? It goes in that direction, okay, as omega increases from 0. And so what we've done here is map these points here specifically into the G of S plane. This is the imaginary, and this is the real. Right, so it starts out purely real, and angle 0, which is this point right here. Okay. Okay. So if you want to map the rest of this, this is at an infinite distance. Points along this contour are at an infinite distance from the origin, right? And therefore, what do you expect 1 over s plus 1 to be equal to?
0.
0, right? So all of these points here, all the way down to there, map into the origin, which is here, okay? And what I was saying earlier was that, the point above here is the complex conjugate of the point below. And if you evaluate the function at that point, well, in fact, what we know is that all of these points map into the origin. Right? So I guess the point here would be is that points down here are complex conjugate of points up there. And so the function, when it's evaluated at the complex conjugate, will just be the mirror image of the point that we already had from up above. So in other words, if you consider frequencies, that are negative, right? In other words, if we started at minus 100, we're coming up from minus 100 towards 0. Right? You start at minus 100 and then you go minus 10 and 5 and so on, all the way up to 0.1. The values that you get will be the same in terms of magnitude, right? This will be 0.01, this will be 0.1, but the phase will just be the negative of what it is here. Right? That's the complex conjugate. Right? So this will be 89.4, this will be minus 84.3, and so on. The 5 will be these are all plus, right? So this will be plus 79. magnitude is 0.2. So when you plot those, basically what you're going to get is, at this point here corresponding to 0, right? And so for negative values, you'd have this contour here. Okay, so we started at that point, we went up the j omega axis, we mapped this segment here, and then we went around this infinite radius semicircle, and they all mapped into the origin here. And now we're going up the j omega axis, right, and we map these points here, right, so we have several points here. And so this is the complete mapping from this closed clockwise contour in the S-plane to a closed, turns out to be a clockwise contour in the GH plane, right? So we're going to use this later to determine closed loop system stability. Okay, it turns out that if this contour makes no net clockwise encirclements of the point -1, then the system will be stable. Okay, but what we have to do is present what's called the Cauchy principle. It's also called the mapping theorem. The mapping theorem before we can kind of put this together. So, are there any questions about the mapping here? Yeah.
Could you explain again why the semicircle portion maps entirely?
Yeah. The magnitude of S is infinite on this contour here, because it's an infinite radius contour. And here you've got an S in the denominator, and it's infinite. Okay, and that will be true for most rational functions, because the order of the numerator would be less than the order of the denominator. In this case, see, this is true in this case, and it's true for most cases. This is the first order. That's a order 0. Okay. Yeah. So actually, all we have to do then is map points along this positive imaginary axis and then along this contour here. And we can, once we have that, we just take whatever we found here, which was this, and then the origin, we take the mirror image of that. And so about the real axis, so it flips around like that. And the what do you call it, the direction is going to be consistent. It's not going to change direction. Okay. So in other words, this closed clockwise contour produced another closed, and it turned out to be clockwise as well, but that's not always true. And later, what we're going to see is that as long as the net number of clockwise encirclements about that -1 point is 0, then we can determine system stability in many cases. And I'll be more specific as I go along. Okay, so what we want to do now is consider, this mapping theorem, the mapping theorem. And I'll close this. this mapping theorem will lead up to what's called the Nyquist stability criterion. Okay, and the Nyquist stability criterion, from that we can determine system stability. Okay, so the mapping theorem also called Cauchy principle. All right, for this, we consider an arbitrarily selected closed clockwise contour. So it doesn't have to be this one. It's going to be in the S-plane, arbitrarily selected closed clockwise contour. Okay. Okay, so it's in the S-plane, right? And so let me select a specific contour, okay? That it could be, and it is, I arbitrarily selected it, right? So let this point be -2, and this point here -J1, this point here J1. So it's going to look like this. It's going to be closed clockwise contour. So it goes all the way out to -6. So this is -2, -4, -6. Okay, so, and then it closed clockwise contour. Okay, and encloses Z zeros and P poles of some rational function f of s. So let that rational function be this one here. F of s is equal to s plus 1, s plus 5, okay, divided by s plus 3, and then we have s plus 1 plus j1, and s plus 1 minus j1. It's complex conjugate. Okay, and let's put the poles and zeros on here in the S-plane. Show those poles and zeros. So we have two zeros at -1 and -5. So we have a 0 at -1. This is this point here is -2, -3, -4, -5, and -6. So we have a 0 at -5 and a 0 at -1. Put those in. We have a pole at -3. So here's a pole at -3. And we have complex conjugate poles. The poles would be at -1 minus j1 and -1 plus j1. Right? In other words, we set each of these factors to 0. And so we get -1 plus j1. We have a pole there. And we have a pole there. Okay. So we have this arbitrarily selected closed clockwise contour that encloses z zeros and p poles. So what is z equal to in this particular case? 1. So z equals 1, and p also equals 1, right? And notice that it's not enclosing those poles and 0. Okay. So what we want to do is another mapping, right? This mapping now from points on this contour into the plane of f of s. Right? So we have the f of s plane here, the imaginary a component of f of s and the real of f of s. Okay. And if we take the points starting at -2 and then -2, minus j1, -2, -3, minus j1, -4, minus j1, -5, minus j1, this point, and then this point, okay, and then we take the mirror image of the points. In other words, we would take that point there, that point there, that point there, that point there, and map them into the plane, the f of s plane. What we would have in this particular example, what it would look like is something like this. It would be a closed contour that turns out to be roughly like that, okay? And the direction is like this, okay? The question is, well, let me say that the Cauchy principle states that n is equal to z minus p. Right? That is the Cauchy principle, where n is the net number and is equal to the net number of clockwise encirclements about the origin of f of s. Okay, so what is n equal to in this case? 0. There are no there are no encirclements, period. And, I mean, and as far as net number is concerned, it could be that there is for a specific problem, there could be one clockwise encirclement and then a counterclockwise, and then the net number would be 0. Okay, for example. But here we have 0. N is equal to 0. There are no encirclements about the origin. Oh, and what this does here, it basically predicts what n will be, right? And z zeros and p poles of f of s are enclosed by this contour. So z is equal to 1, p is equal to 1. Therefore, n will be equal to 0, 1 minus 1, right? And so basically, like I said, this predicts what n will be. And this is the actual mapping. And you can see that there are no encirclements about the origin of f of s. Okay, let's take another example. And this one, I have the M file for this, but this is the basic idea, and that's what I want you to get. The mapping. In other words, if you map -2, right, into the plane of the open, into the f of s plane, what do you get? You just substitute -2 in here, so you get -1 times 3 divided by, this will be s squared plus 2s plus 2 if you multiply it out. And so here 3 minus 2 is 1. And then here -2, that gives you -2, it's going to give you 4 minus 4 plus 2. So that just gives you a 2 there. And so here you're going to get -3 halves, right? -3 halves, which would be this point right here. Okay, -3 halves. And then you would take this point here, -2 minus j1. You substitute it into that. You find the magnitude and phase of that, and you plot a polar coordinate, right? It has a certain magnitude and a certain phase. Just like over here, we plotted magnitude and phase to get this diagram over there. Okay. So let's take another example. Yeah, a quick example is this one here where we have the closed clockwise S-plane contour. This is the S-plane. And the points on this S-plane contour are J1, and then 1 plus J1. This is 1. Okay, so this is minus J1. This is minus 1, minus J1. Okay, so there are several points that we can take. We can take these corners. We can take these points here. Okay, and what we'd like to do is consider the mapping of this simple function 1 over S. Okay. And notice that here there's a one pole right there at the origin, right? And so what is n equal to? It's a z minus p. And z, there are no zeros, and there is one pole, right? So this is equal to minus 1.
Encircles the origin, but it does it counterclockwise?
Well, we'll see. We'll see. It's true, yes, counterclockwise because it's minus 1. It's one counterclockwise encirclement about the origin is a prediction. Okay, so let's do it. Let's see, where's my well, here this is the f of s plane, right? So f of s plane, right? So we put in 1, we get 1, right? So there's say 1. We put in 1 plus j1, we're going to get 1 over 1 plus j1, right? That's going to be the magnitude square root of 2, and the phase is going to be minus 45, right? Oh, sorry. It'll be plus 45 because the point that we're taking is 1 minus. We're going to take it in the, this is, remember it has to be a clockwise, closed clockwise contour. So we started here, we have to go to that point there. So that's 1 minus j1. So 1 minus j1 is going to give us, this would be minus 45. And when it goes, the reciprocal is going to be plus 45. Right? In other words, 1 over square root of 2 e to the j, minus j45 is 1 over square root of 2 e to the j45. So it gives a point right there. Right? And then we take this point minus j1. Minus j1, what does that give it in terms of magnitude and phase? There. 1 over minus j1, right? 1 over minus j1. And if you rationalize it, you can multiply top and bottom by j, and this becomes j1. It becomes j1. And that is basically this is the same as 1 angle 90 degrees, right? And so that's right here, j1. And now we can see the direction. As we moved from this point to that point to that point, we went from here to there, and therefore the direction is like that. Okay. If you continue with this, what you get is a point here, a point here, here, and here. So you get this. And here's the origin, right, of the f of s plane. So we map from the s plane to the f of s plane. How many encirclements of the of the origin do we have? It's one, and it's counterclockwise, right? You can see it's counterclockwise, and this predicts that it's counterclockwise. Right? You get one counterclockwise encirclement because it's negative. Okay. Okay. So what we're going to do now is apply this mapping theorem to the determination of the closed loop system stability. Okay. So apply the mapping theorem to determine closed loop control system stability. Okay, so here's our closed loop control system here. We have the G and the H. And the closed loop transfer function, TCL, say, is equal to C over R, where this is C, this is R, and this is going to be equal to G over 1 plus GH. Right? And then let's just call this 1 plus GH, call it F, or F of S. So we've got G of S over F of S, where the F of S is equal to 1 plus GH. And what you see is that the pole of the closed loop transfer function, right, is determined by finding the zeros of this characteristic of this f of s. Right? If you want to find the closed loop transfer function poles, you set the denominator equal to 0, right? So you set that equal to 0. The poles of the closed loop transfer function are equivalent to the zeros of this f of s. So the closed loop transfer function poles are equivalent to the zeros of f of s. Okay, and so now GH here, G of s, H of s is a rational function. What that means is the ratio of polynomials, right? So let's say that is equal to numerator over denominator polynomial. Now, and therefore f of s is equal to it's equal to 1 plus gh, right? But gh is equal to numerator over denominator, and therefore this is equal to numerator plus denominator over denominator. And so what I'm trying to say here is that the poles of the open loop transfer function are the same as the poles of f. Okay? So the poles of G of s, H of s are equivalent to the poles of Yes. And typically, we know what the open loop transfer function is, right? We typically know the transfer function GH. And so we can determine from that transfer function the poles of GH. And if we have the poles of GH, we also have the poles of F. And notice that F is a rational function. It's a ratio of polynomials. Okay. Okay. So now let's apply the Cauchy principle, this mapping the theorem here. We have the S-plane contour of interest as far as closed loop system stability is concerned is the one that I've shown there, and we draw it here. So it goes up the J omega axis all the way to J infinity, right, up there, and circles the whole right half plane. This is infinity here. It's a closed clockwise contour. Goes back up the J omega axis. Right, this is minus J infinity. Okay. And we're going to apply the mapping theorem. The mapping theorem states that n is equal to z minus p. And n equals z minus p for z is equal to n plus p, right? Z equals n plus p. And here, p will be equal to the, see, this is the right half plane. This contour here encloses the whole right half plane. So p is equal to the number of right half plane poles of f of s, right? And p is likewise equal to the number of right half plane poles of GH. Because that's just what we said here. The poles of GH are equivalent to the poles of F. And Z, for this particular contour here, is equal to the number of right half plane zeros F of S. And you see the closed loop transfer function poles are the zeros of F of S. What do we want Z to be equal to? That's the question. What do we want Z to be equal to? The number of right half plane zeros of F of S, same as the number of right half plane closed loop transfer function poles, plus 1, what's that? P plus 1.
So that n.
Actually, I mean, we want Z to be equal to the right half plane poles. The number of right half plane poles should be what for stability? 0. So that's the same as the zeros of F of S, okay? So we want no zeros of F of S in the right half plane, right? Z is equal to 0 for stability. Okay. This is for closed loop system stability, right? I'll just put in there closed loop system, closed loop system stability. And so we want this to be 0 we know what this is. In order to determine what z is, we have to know what n is. Okay, so the whole objective here is to determine n. N, remember, is the net number of clockwise encirclements made about the origin of the f of s plane contour. In other words, when they're mapping from this plane to the f of s plane, this is the f of s plane, we find n by counting the net number of clockwise encirclements about the origin of f of s. That gives n. If we know n, we already know what p is. All we have to do is take a look at the open loop transfer function. Right? If we find n, we know p, we can find z. And so that's what we want to do. We want to determine if the system is stable or not. Okay. Now, the last step, remember that f is equal to f of s is equal to 1 plus gh. Right? So instead of mapping from the s plane here, the s plane to the f of s plane, we can map from the s plane to the gh plane. Instead of counting encirclements about the origin of f of s, we can count the number of encirclements about the point -1, because gh, the gh is equal to f minus 1. Right? So basically, it shifts the plot to the left by 1. Okay, so instead of counting encirclements about the origin of f, you can equivalently count the number of encirclements about the point -1 of gh. Okay, and if you go back to this problem here, this is, we did plot gh because the h was equal to 1, and so the -1, how many net clockwise encirclements about the -1 do we have? Here's 0, right? So n is equal to 0. And so if n is 0 and p, the number of right half plane poles of gh, how many right half plane poles of gh do we have, if any? Are there any poles of gh in the right half plane here? No. So p is equal to 0. So p is equal to 0, n is equal to 0, therefore z is equal to 0. And therefore this system over here is stable. Okay. So, you know, what we're doing is mapping from this contour here, this is the S-plane contour enclosed in the whole right-half plane, into, instead of the S plane and counting encirclements about the origin, we'll map into the GH plane and count encirclements about the point -1. That gives us the n value there. Okay, so we'll continue with some examples next week.